Hello, everyone. Today, we will delve into Chapter 2, Fundamentals of Cryptography and Blockchain. This chapter covers Bitcoin blockchain, overview of cryptography, symmetric cryptography, asymmetric cryptography, and hash functions. First, let's start with Section 1, Bitcoin blockchain, overview of cryptography. The reference architecture of blockchain is mainly divided into 6 layers: the application layer, contract layer, incentive layer, consensus layer, network layer, and data layer. The 3 layers at the bottom are especially important. From bottom to top, the data layer includes data blocks, chain structure, timestamps, hash functions, Merkle trees, and asymmetric encryption. The network layer includes P2P networks. The consensus layer includes consensus algorithms such as POW, POS, DPoS, PBFT, and others. In modern cryptography, the primary principles include 4 key aspects: confidentiality, integrity, authenticity, and non-repudiation. Confidentiality is mainly achieved through stream ciphers and block ciphers. Integrity is mainly managed using hash functions. Authenticity is mainly provided through message authentication and entity authentication. Non-repudiation is primarily achieved through digital signature technology. Next, let's look at the 3 stages of the development of cryptography. The first stage, before 1949, is called classical cryptography. Cryptography during this period was considered more of an art than a science, as it mainly involved manual operations. The main characteristic of this era's cryptography is that its data security was based on the secrecy of algorithms. Classical encryption methods primarily involved substitution and transposition, implemented through manual or mechanical transformations. The representative ciphers include the monoalphabetic substitution cipher, polyalphabetic substitution cipher, and rotor cipher. One of the most famous examples is the Enigma cipher, which was invented by Germany during World War II. From the following images, we can see that some cipher machines from the World War II period were based on manual operations, with the right one showing a rotor-based mechanism. The second stage of cryptography development, from 1949 to 1975, had a major milestone in 1948, when Shannon published his paper A Mathematical Theory of Communication in the Bell System Technical Journal, laying the foundation for the famous information theory. In 1949, Shannon published The Communication Theory of Secrecy Systems, which laid a solid theoretical foundation for cryptography, transforming it into a true science and marking a major shift from cryptography to cryptology. The main characteristic of cryptography during this second phase was that data security was based on the secrecy of keys, rather than the secrecy of the algorithms themselves. The third stage, from 1976 to the present, saw Diffie and Hellman publish their paper New Directions in Cryptography, which proposed a revolutionary new approach to cipher design. This marked the beginning of a revolution in cryptography. They were the first to propose the public key cryptography, breaking the constraints of traditional symmetric key ciphers. Traditional ciphers primarily focused on the confidentiality of information, but the new public key cryptography not only ensures communication confidentiality, but also provides message authenticity. The new double key encryption eliminates the need for pre-shared keys, enabling the secure transmission of information over insecure channels and significantly simplifying the key distribution process. Next, let's take a look at the components of cryptology. First, let's explore the concept of cryptology. Cryptology is the study of encoding and decoding messages. It mainly consists of cryptography and cryptanalysis. Cryptography focuses on how to encode information to conceal it, while cryptanalysis involves deciphering or forging ciphers, including cryptanalytic attacks and brute force attacks. The basic terms in cryptology include plaintext, ciphertext, encryption, decryption, key, eavesdropper, cryptanalysis, and cryptanalyst. A mature cryptosystem, commonly referred to as a cipher system, consists of 5 components. The first component is the plaintext space, abbreviated as M, representing the set of all plaintexts. The second component is the ciphertext space, abbreviated as C, representing the set of all ciphertexts. The third component is the key space, abbreviated as K, representing the set of all possible keys. The fourth component is the decryption algorithm, abbreviated as D, representing a set of transformations from ciphertext to plaintext. The fifth component is the encryption algorithm, abbreviated as E, representing a set of transformations from plaintext into ciphertext. Next, let's explore the process of encryption and decryption. The encryption process involves transforming plaintext into ciphertext using the encryption algorithm. During this process, the encryption key is also used. After the plaintext is encrypted, the ciphertext is transmitted to the recipient. Upon receiving the ciphertext, the recipient uses the decryption algorithm and the decryption key to decrypt the message, recovering the plaintext. Therefore, the operations of encryption and decryption algorithms are usually performed under the control of a set of keys, known as the encryption key and the decryption key. When it comes to deciphering, one of the most important algorithms is brute force attack, also known as exhaustive search. This means trying all possible keys on the intercepted ciphertext until meaningful plaintext is obtained. Another method involves encrypting all possible plaintexts under a fixed key until a match with the intercepted ciphertext is found. Theoretically, as long as there is sufficient computational time and storage capacity, success is always possible in principle. In practice, any encryption system that meets security requirements will be designed to make this method practically unfeasible. Thus, we need to understand 2 important concepts. The first is absolute security. Absolute security means that no matter how many ciphertexts are available to the attacker, all of which are generated by a particular encryption algorithm, the information contained in these ciphertexts is insufficient to uniquely determine the corresponding plaintext. Regardless of the attack techniques used, the encryption cannot be broken. In real-world situations, except for one-time pads, there is no encryption algorithm that offers absolute security. The second concept is computational security, meaning that the cost of breaking the cipher exceeds the value of the encrypted information. For example, if decrypting the cipher requires 10 million computers to run calculations simultaneously, the cost is extremely high. If the value of the information is not enough to offset the cost, then such decryption is not worthwhile. The second point is that the time required to break the cipher exceeds the useful lifespan of the information. As we discussed earlier, a brute force attack works by continuously testing all possible keys, or plaintexts, to find which one corresponds to the ciphertext. This method is extremely time-consuming, and in some cases, it can take decades, centuries, or even thousands of years to break. In such a lengthy time frame, even if the cipher is eventually decrypted, the information becomes useless. For example, if it takes 1,000 years to decrypt, the decrypted information would have no value by that time. So, the design principles for evaluating a cryptosystem mainly include the following aspects. 1. Computational security. This means that the most effective attack algorithm for a cryptosystem takes at least exponential time, also known as practical secrecy. 2. Provable security. If the security of a cryptosystem can be reduced to a mathematical problem that is difficult to solve, it is considered provably secure. 3. Unconditional security or perfect secrecy. This means that assuming an attacker has infinite computational power, if the cryptosystem cannot be broken by such an attacker, it is called unconditionally secure. Thus, the design of a practical cryptosystem should adhere to the following principles. 1. Cryptographic algorithm security. The strength of the algorithm should be high enough to make it computationally infeasible for an attacker to determine the key or any plaintext from intercepted ciphertext or known plaintext ciphertext pairs. The term computationally infeasible means that it is practically impossible in reality. For example, if it requires the use of 10 million computers and takes 100 years to compute, then it is not feasible in the current real-world context. 2. Kirchhoff's principle. The security of a cryptosystem should not rely on the secrecy of the encryption algorithm, but rather on the key, which can be changed at any time. Since the 1970s, this encryption principle has been the foundation of most cryptosystems, focusing on the key rather than the algorithm itself. 3. Sufficiently large cryptographic space. This makes it computationally infeasible to search for the key using brute force methods. In other words, brute force searching the key space should not be computationally feasible. 4. Ease of implementation and use. Both the encryption and decryption functions should be computationally efficient. This is primarily reflected in the mathematical aspects. We have now completed the first section of Chapter 2. Thank you, everyone.